Yeah, it's fun experience. Yeah.
Until you sit down and then it
Thanks for
I'm losing track of time.
All right, everybody, welcome. Thank you all for coming, especially for those who make out of town. Great event. So I need to say a couple of acknowledgements. The event is sponsored by Fine Credit of Physics Institute and by Simon's Foundation. General grant funds. Simon's allowed that. So you're all welcome to acknowledge it in your publication if anything comes out of it. Now, the idea was to bring people from different communities, and that's a sort of risky adventure. We hope it will work, but I ask all the speakers to do an extra effort to be accessible to people who never thought about your stuff. Thank you. Now, a few organizational things. Then we go for lunch, and for lunch you're on your own. So the good idea for lunch is to go along Washington Street east. So you can leave your bags in a break room that we just have breakfast. Schedules are posted here. There are whiteboards in a break room for discussions, and there are poster easels there. So if you came with poster, you're welcome to hand at any time. The sooner the better. We will have dedicated time tomorrow. Last but not least, today at 6 p.m. we'll have a conference dinner at Alumni Center. Check your website. Tell you direction. It's 5 minutes walk from the church. All right. So then without further ado, the chairman of the first session is Bill Pepperman from Chicago, and he is the boss now.
Okay, so welcome. The first talk, we have Liang from MIT, and he's going to talk about connections between AI and matter.
Good morning, everyone. I'd like to first thank the organizers for not only inviting me, but also, allowing me to talk about something about classical computer in this workshop focus on content computation. So I'm hoping to really learn from other talks. So maybe a year from today, I can talk about AI for content computing. Anyway, so the talk is about our recent work using AI for studying quantum matter and predicting new quantum state matter. Unlike large language models that learn from internet text, here the method we are going to talk about is all based on the first principles quantum mechanics. It does not require any external learning data. So let me first thank all my collaborators. Last 2 years, Tim, C, Pierre, Anton, and Patch, PhD students, and Patch was the thesis. Filippo, Max, and Ahmed are postdocs. So when they joined my group about 3 years ago, everyone is working on different projects. And then over the last 1.5 years, we all converged into this direction. And a lot of this is motivated by the work of Otten. He was an undergrad at UK Cambridge University, and worked with me remotely on the fractional quantum Hall project in AI. And really, all these results got us all excited. Okay, so for this audience, all know that not only fundamental computers are quantum, but really all materials are quantum. We all know that matter are made of atoms, atoms are made of electron and nucleus, and materials such as semiconductors, magnets, superconductors are scientifically interesting, but also they are the basis of modern technology, and all their intrinsic functional properties arise from quantum laws of physics on this level of electrons. For example, in semiconductors, the strong temperature-dependent resistivity is a consequence of energy gap in the electron spectrum, band gap. In magnets, electron spins spontaneously ordered into the same direction, giving rise to spontaneous interbreaking. And in superconductors, electrons, despite repelling each other, are able to form pairs, and these charged three-focal pairs condense into a single quantum state that enables the flow of current without resistance. So ultimately, all these quantum phenomena, emerging phenomena of materials, can be traced to this single equation, which is the many electron Schrodinger equation. This equation describes the behavior of electrons in solids. So the energy operator, the Hamiltonian, consists of kinetic energy of electrons, as well as the interaction, the repulsion between electrons, and the Coulomb interaction between electrons and neutrons. So in principle, if we can solve this many electron Schrodinger equation, we find the lowest energy state. This ground state really encodes a wealth of information about the system. In fact, it's fair to say that it encodes complete information about low temperature properties of the system, such as the total energy, the original state, the degree of spin polarization, and from the two-particle reduced density matrix, we can detect the presence of superconductivity. So that's why we're going to focus on the ground state, many electron system. And moreover, by inspecting the topological properties of the wave function, leads to the concept of topological states of matter, including topological integers and fractional transistors. And here we're even able to predict materials for these states before they were experimentally realized. Now, okay, so the challenge, of course, solving this many electron Schrodinger equation is extremely difficult. It remains one of the last unsolved problems in computational physics and chemistry. And as you all know, that this has to do with the quantum nature of things. We have classical particles. The configuration is specified by just n variables, the position of each particle. But in a quantum system, we know that you can have the superposition principle. Particles can be here and there at the same time. So instead, the description is that for a given set of particle coordinates, there is a probability amplitude psi, which is basically a quantum wave function. So to specify a quantum wave function is way harder than specifying just a set of particle coordinates. And in fact, even if you have a one particle system, to completely specify a function of a single variable requires infinite numbers. For example, you can find a basis, you expand the wave function in the spaces. For particles in continuous space, you need infinite numbers because there are infinite basis states. If we have n particles, then the space of all possible wave functions is really infinity raised to a dimension of 3n. Right. So this is a very difficult problem. Now, for a given wave function, one can actually compute the corresponding energy excitation value by Monte sampling, but this is not hard. And in principle, if you can search within the space of all possible wave functions, and if the optimization can be done, then you can arrive at the ground state by variational principle. But the real challenge is how do we explore the space of infinite-dimensional wave functions? Now, that's not to say that we don't understand anything. In fact, the physicists have long been extremely successful in using approximate wave functions to understand the nature of the different phases. For example, the theory of conventional metals and insulators are based on this idea of a scalar determinant, which is equivalent to Hartree-Fock theory. Basically, instead of dealing with a full many electron wave function, we approximate wave function as a determinant of one particle orbitals. Okay. And another example is the theory of conventional superconductivity, I think Cooper-Schrieffer theory. Here, we focus on a wave function based on electron pairs. So it's expressed as a Fabian of this two-particle wave function G. GRI-RJ describes the wave function of a Cooper pair. And so in both examples, you see that the full complexity of a particle function is enormously compressed. It's now built only using one particle or two particle building blocks. So these wave functions are large part of the basis of a large part of solid state physics, and these are ingenious product of the human mind. But of course, there's also some challenges. So we take these wave functions at face value, they are not quantitatively accurate. And also we see that different states of matter requires very different forms of wave functions. From the state of determinant, you can never get superconductivity. So in that sense, there's a lack of generalization and there's a lack of unification. Now, before I move on to AI, let me just further say that in some sense, right, this amount of a compression is what we do all the time in physics. And there's a quote that's widely attributed to Landau. He says that with 4 parameters, I can fit an elephant. With 5, I can make him wiggle his trunk. Right? In that sense, it captures this philosophy that less is more. And actually, people try. And this is a paper I found by talking to ChatGPT. These authors were actually able to fit an elephant using 4 complex parameters, 8 real parameters, and understood. But of course, you can compare with an image generated by ChatGPT, and you see that now I think we can do more and more. Okay, so that's the idea. Because wave function is so complex, we want to use a neural network to approximate wave functions. And the way it works is that you take the particle coordinates as inputs for every particle configuration. These coordinates are embedded in high-dimensional space. That's called the latent space. And then the neural network performs a set of transformations, the linear transformation and the nonlinear activation, layer by layer. And eventually, this high-dimensional vector is further projected into a 2-dimensional space that describes the real and imaginary part of a complex wave function. And what's remarkable is that neural networks turn out to be extremely expressive. They can approximate very complicated functions rather well. That's a basic idea. And instead of having the wave function being analytical or elegant function of particle coordinates, such as later determinant or PCS wave function, here the wave function is expressed in terms of all these weights and biases. These are the parameters that define the variation of wave function. Okay. Once you use the neural network to generate the wave function, you can then compute the energy excitation value through Monte Carlo sampling, and then one can ask neural network to update the weights and biases in order to systematically lower the energy. And this is the optimization. Optimization problem. It's based on the optimization problem, and in practice, it's often done by the gradient descent. And you can see that here we're combining neural network and Monte Carlo to solve the long-state problem. And this is really a self-supervised learning method. There's absolutely no training data at all. The only information about the physical system is in this loss function, which is defined by the energy. For different materials like aluminum or copper, the nuclear positions are different, the nuclear charge is different. More enters. Other than that, there's no physics input into this. Okay? And this idea of using neural network and Monte Carlo to study quantum matter has started already quite some time ago. About 10 years ago, with former group members, we used neural network to speed up the Monte Carlo sampling for sign-free lattice models. Liang and Troyer introduced this variational Monte Carlo to search for the ground state. And very important, nice work by Lilo and Brian Clark. Brian is here for lattice models of fermions. Now, for the rest of the talk, I'm going to, what we are doing is, at least initially, very much inspired by the work of Google DeepMind, led by David Fowle, and they were among the first to do this variational neural network method for studying the ground state of atoms and molecules. This is really many electron Schrodinger equation in continuous space, and that is the subject of my talk, not just for molecules, but for solids. But before that, yes.
Can you say a little bit just about the counting of the parameters? So obviously, a Slater determinant,
Right.
has very few variational parameters, but like, you also can't get the full Hilbert
Yeah,
space.
that's
of the
exactly what I'm
particle.
talking about.
Okay.
Absolutely. So, now in some sense, it's perhaps not surprising that more parameters, for example, we very often use hundreds of thousands or million parameters. It's not a surprise at all that with more parameters can get better variational energy. But I want to raise a question exactly Fiona is asking. As a theorist, right, we would like to ask a more fundamental question. Can neural network solve many electron Schrodinger equations exactly, or to be more precise, asymptotically exactly? Meaning that as the network size increases, and we systematically approximate any from say wave function to arbitrary accuracy. So that's a question I want to ask. Okay. And this problem was not addressed in any of these previous works. And again, assuming optimization can be done perfectly. So this problem really reduces the following problem. Can large neural network approximate any Fermi wave function to arbitrary accuracy as the network size increases? Okay. Now, you may have heard something called the universal approximation theorem, saying that neural network can approximate any continuous function on the compact domain to arbitrary accuracy as the network parameter increases, number of parameter increases. And here, we're dealing with a problem of a different kind. Remember that the wave function for electrons is not just an any function. It has to satisfy the fermionic anti-symmetry. If I change two particle coordinates, the wave function has to take a minus sign. So the standard universal approximation theorem does not enforce this anti-symmetry. So we cannot use it directly for solving any electron wave functions. So this leads to the question, is there a neural architecture that exactly enforces anti-symmetry by design and also retains the universal approximation power in the sense that it can approximate any continuous fermionic anti-symmetry on compact domain to arbitrary accuracy, provided sufficient size? Yes, Alex.
So the question is, you keep system size fixed,
Keep system fixed, exactly.
increase size of your neural net.
I always work with a finite system. Yeah, and in fact, I strongly believe that that is important. Discuss later. Yes.
And so you're only interested in asymptotically large size of network, but not how it scales with the system size?
I will talk a little bit about that. Yeah. But even this question, right? So now it really is a mathematical question. Okay, so is there a construction that enforces anti-symmetry by design and yet achieves universal representation power? Okay. And here's a result I came up with. Got obsessed with this problem, and actually this problem has previously only been studied by two mathematicians. And I'm not going into the details. You can find reference here. But it turned out that the previous work it's not very efficient. And here I'm presenting my method. Okay, so the way we're going to do this is very simple. We're going to basically first transform particle coordinates into some set of collected coordinates called C and eta. So C is a symmetric function of particle coordinates. Eta is an anti-symmetric function of particle coordinates. And we want this C and this mapping from particle coordinates into C and eta satisfies some properties that I'll specify in a minute. But then, in order to ensure the anti-symmetry, all we need now is want the function f, a function defined in the space of C and eta coordinates, to be odd in eta. Okay, because when you exchange two particle coordinates, the C stays the same, eta changes sign, and if f is odd in eta, it automatically changes sign. So this guarantees the harmonic anti-symmetry. And constructing an odd function is very easy. You just take any function and minus itself, evaluate at minus eta. So this combination ensures anti-symmetry. So in a sense, what we want to do is we want C and eta to be a set of collected coordinates that's defined in symmetric space, tensor with odd space. So basically, what we want is that the C coordinates completely determine the particle configuration up to permutation. And then because eta is odd, eta will distinguish even odd permutations of the particle coordinates. So this leads to a faithful representation of.
So the answer is yes.
What's that?
The answer is yes.
No,
One can do it.
One can do it, yes. Yeah. how is different from Slater? I'll show you next slide. Yeah. Yeah. Okay. So now, so this construction guarantees antisymmetry, but one can further ask, is this construction universal? In order for it to be universal, what we want is we want to see the mapping from particle coordinates to symmetric functions to be an injective mapping, meaning that every two distinct particle configurations map to different eta, map to different C vectors up to permutation. And we also want this eta function to be non-zero for every collision-free configurations, meaning that provided that the particle coordinates are all distinct, then we have to faithfully track the even odd permutation of these particle coordinates. And we want eta to be non-zero, because if eta is non-zero, plus eta and minus eta corresponds to the even odd permutations. So this will allow us to faithfully keep track of all the configurations. Okay. Now, only very recently, computer scientists have shown that the mapping from this particle configurations, mod permutation to the C space, this injective map can be achieved with only of order n functions. And I'm not going into the details, but you can find in this paper. Then the remaining question is, can we find antisymmetric functions that is finite, that's non-zero for every collision-free configurations? Okay. Now this reminded me of the problem of quantum Hall functions. If you take the in 2 dimensions, if you take, for example, the complete field though it's non-level, the wave function can be written in this way. It's a part of vi minus vj, where z is the complex coordinates. So this polynomial vanishes only when particles coincide. So for every non-collision configuration, it stays finite. So this will immediately do the job. So in 2 dimensions, a single quantum Hall wave function can be used for this eta function, and it only has 2 components, the mu and imaginary part. And then combining that with of order n perceived patterns, we can achieve the exact universal representation and with latent space dimension of order n. And it turned out this is also true for all spatial dimensions. I won't go into the details. Okay. Now, with this, I started experimenting this construction using this quantum Hall wave functions. It works very well for quantum Hall problems, but for other problems, it failed miserably. And in hindsight, it's because whenever you use a fixed form of a basis function, it bakes in too much inductive bias and it makes the training miserable. Okay. So that's why we have to go one more step. Notice that the quantum Hall wave function can also be written as a determinant of single particle lambda orbitals. Okay. And this led to another generalization. So if a determinant of certain orbitals already guarantees universal representing power, we can further promote it into a general determinant, a determinant of general single particle orbitals. So this led to the following representation, that any antisymmetric function can be approximated with this form. There is a determinant part, which basically allows for the most general nodal structure, and then it's weighted by a symmetric function, which carries the full complexity of the n-particle wave function. Importantly, the number of stated determinants is small. The number of determinants k grows at most linear close n. Okay. And with this, we can get a representation that is systematically improvable. As the network size increases, this can approximate any fermionic wave function. It can be ground state and can be precise states. So that's that's the first part of this topic. I call this architecture Fermi sets. The determinant captures the Fermi statistics, and the permutation invariant part is what computer scientists call sets. And in practice, we use a simple feed-forward neural network to approximate single particle orbitals in the determinant, and we use attention mechanism to approximate the fully general symmetric orbital symmetric functions, and basically we take the transformer architecture with symmetric cooling. Yes.
Can you go back one slide? This form of the wave function looks naively to me like a CI expansion. configuration interaction expansion. A sum of coefficients times a bunch of determinants.
The important thing that this the prefactor here is not just coefficients, it's a function. That's a key difference. So the usual expansion in terms of state determinants, the coefficients are numbers. Here, those prefactors are symmetric functions of particle coordinates, and that is crucial.
It's much closer to like a multi-Slater gesture.
Okay. So there's a difference. Also different with the multi-state gesture. The usual gesture is positive definite, and here in order for this to work, we need the wave function to be fully complex. That's
People have run RBMs for that gesture. But certainly the standard gesture is positive.
sorry, Steve.
I said people have used sort of complex gestures using RBMs and things, but the standard gesture is positive.
Yeah. But the important statement here is that there's a universality guarantee. Okay? With this structure, using of order n terms, we can universally approximate any entanglement function.
Is it unique?
No, it's not unique. What do you mean unique?
One unique.
What do you mean by unique?
I assume in contrast to expansion over Slater determinants, this expansion is not unique.
It's not unique. It's not unique. For example, you can easily find different phi and omega that give you the same wave function.
You should want unique.
But this is always the case. So the neural network, when you do the optimization problem, you can very often get a different parametrization of the same wave function, or almost the same wave function. But what we care in the end is the wave function. All these parameters, phi and omega, are just parameters. At the end of the day, we just care about wave function. In the end, everything is very explicit. Once the network is optimized, you put in the particle. You can query the neural network, right? For any particle coordinates, what is the corresponding amplitude? It will give you the amplitude. So that's what's critical. All right. So let me now show you some results. So as a first test, we look at this problem of the interacting electron in the 2D harmonic potential of quantum dots. And this problem is specified by particle number n and interaction strength lambda. And for a small particle number, we compare the Fermi sets calculation with conventional methods, RP4, flow, and you see that the energy is always better. Also, notice that our neural network, we do not take into account any symmetry condition. The neural network just lowers energy, and whether you get a symmetric state or different state, whatever the ground state is, we try to get that. But in this case, for 6 particles, you see that in the end of the charge density distribution in real space is rotationally symmetric. Okay, so far.
Because it's my magic number or something.
Yeah, I'll come to it. I'll come to it. You anticipate this. It's a closed shell. It's closed shell. Right. Yeah. So so far, right, what I've been talking about is basically for every problem, you can initialize a neural network and you do this optimization problem, it finds a ground state. And this is actually a very limited use of neural network. The true power of AI is the ability to generalize. Right. So my student team, initiated a very ambitious project. Me. So we want to ask a question that can we solve a whole class of problems that depends on Hamiltonian parameter lambda. Okay. So here's what we found out that we can basically condition this whole neural wave function on Hamiltonian parameters. The Hamiltonian parameters also enter the neural network, and this allows us to build a unified foundation model to solve multiple problems with different parameters lambda. And after solving this problem, the neural network actually learns how the ground state wave function depends on the parameter lambda over a co-continuous range. So it allows us to predict new ground states for unseen parameters without doing any further optimization. So this is why we call it foundation model. And here are the results. So we asked the neural network to solve first the following problem with 6, 8, and 10 particles with interaction strength 0, 1, 2, 5, 8, 10. And after optimization, for example, for 10 particles with interaction strength 5, this is the charge density, symmetric. And then we asked the network to further predict the ground states. We immediately predict ground states for unseen particle numbers and unseen interactions. Here, for example, lambda equals 7 is a prediction, and you see that the wave function is symmetric, but the drop rate is larger because of the strong flow repulsion. I think it was really interesting that for 7 particles, the this is the prediction. 7 is an unseen particle number. For interaction strength 5 and 7, you see that now the charge density shows a 6-fold symmetry. Okay, and this is actually not an artifact. Even though the problem is fully rotationally symmetric, for 7 particles, it's an open shell, meaning that there's a ground state degeneracy between angular momentum 3 and -3. So the neural network picks a linear combination of the two states so that you get a 6-fold solution. So we can, on one hand, I want to emphasize that all the energy that I'm showing you here is not directly output from the network. The network only outputs wave functions, and energy is computed honestly by Monte Carlo sampling of predicted network wave function. And here you can see that for the blue dots are the trained tasks, and all the other data points are the prediction. And we can do this even for 50 particles, trained on a single GPU. So this led us to, ultimately the long-term goal is we want to build a foundation model for matter, molecules, solids, and we want to train this foundation model on a broad range of problems to optimize itself, to solve for ground states. And we want that after the optimization, we hope that the foundation model can predict manage on ground states for any given nuclear configuration. And as a first step, I obsessed with cloud coding, and talking to it, we are able to do some interesting Hall experiment with solid hydrogen for multiple nuclear configurations, both the equilibrium configuration and randomly displaced nuclear colonies, and you get energy that beats previous BMC and DMC results. So in the last maybe 2 minutes, I can briefly show you some new results. Okay, so the neural network not just sort of better at quantitative calculations, but it can even lead to some new quantum state not completely unanticipated before. Okay, so the problem we are studying is basically the problem with electron gas, which is the cornerstone of advanced matter physics. We know that a high density ground state is liquid, low density is crystal. The question is what happens at the intermediate density. Okay. And here's a Hamiltonian. We're dealing with a realistic quantum well with a finite thickness. So we're dealing with a 3D system and whisk-blown repulsion. Okay. And in this case, the problem has two different parameters. One is the interparticle distance in units of ball radius, basically tracks electron density, but also the finite thickness introduces a new parameter, d. And that's why the phase diagram is much richer. And the Filippo and Jiang and Tom have studied this problem systematically as a function of interparticle distance and thickness. And here, the color each points represents the intensity of the Bragg peak. So if you have a high intensity, it means that it's a crystal. Low intensity is a liquid. So at high density, particle density, we see that the ground state is metal, it can be a monolayer metal, or it can be a bilayer metal, electrons spontaneously. In order to avoid each other, to save the Coulomb energy, electrons spontaneously form two layers near the top and bottom of the quantum well. But interestingly, at low density, we found a lot of interesting crystal phase. For example, we get a monolayer Wigner crystal, as you expected. You see these high density peaks form a triangle lattice. At a larger film thickness, what we see is that the electrons on top and bottom layer, they both form a triangle lattice, but they are laterally shifted away from each other. So combining the top and bottom layer, we get a honeycomb lattice. Okay. So these are perhaps not too surprising, but a true unexpected surprise is that at intermediate density and at intermediate quantum well thickness, we find a new state. The electrons on top and bottom layer still form a triangle lattice, but they are 30-degree twisted away from each other for reasons we didn't at all anticipate at that time. And as a result of the 30-degree twist, we get a quasi-crystal. The charge density pattern never repeats. It's not periodic. And we get a 12-fold Bragg peak. Okay. So this is an AI-enabled discovery, electron quasi-crystal. I'm running out of time, so I'll just say that for now, with DA and with Filippo, we now have an analytical theory. Okay. We have now a full theory phase diagram without doing any neural network calculations. We are able to understand the origin of this quasi-crystal, why it can be energetic favored compared to the honeycomb crystal. Punchline is that it's a truly quantum phenomenon. If we only talk about the particle electrostatic energy, honeycomb is always favored, but quantum zero-point fluctuation can actually lower the energy of the polycrystal to make it a true ground state. So I'm going to stop here and speak the cover. Thank you.
Okay, great.
Maybe I have two questions. One is, it seems to do very well in continuum. Is there a version of this that works on lattice problems?
Yeah, sure.
And can it
People have
compete
tried
with
on
PEPs?
lattice
How does it do compared to
Actually,
PEPs?
my
please.
How does it do compared to PEPs? And how many parameters are needed here? That's the other question.
Let me first answer the second question, right? So for example, in most of our calculations, we use less than 1 million parameters, sometimes at most 2 million parameters. And we can reach system size of even 100 particles more on just a single GPU. So the scaling seems to be quite favorable. Now about lattice models, right? So yes, people have tried neural networks, neural wave functions applied to lattice models. And I think for example, the Fermi-Hubbard model, the latest neural network results beats for 16 by 16. For 16 by 16 lattice sites, it beats the tensor network.
I'll flash up some things.
So you train your neural network on a finite size system, but how dangerous are finite size effects? For instance, you train it on a disk, and disk supports for 8 modes.
Yeah.
Then what? Will they survive in the bulk?
Absolutely. So I personally think that finite size study is actually important because if you directly tackle the thermodynamic limit, I think there's no way you find a polycrystal for which the ground state is aperiodic. So instead, I think finite size is really useful, and if we do systematic finite size scaling, to me, I think that's a more reliable approach. It's personal opinion. But you're right that we have to be very careful about finite size effect. For example, if you want to extract the bulk physics, I didn't talk about this here. For example, when we do the fractional quantum Hall problem, we started with a disk, and of course, there's a finite size limitation. But of course, it also gives you things like edge states, which is a benefit. But if we want to focus on the bulk physics, this recent work with Ahmed, we switch to the periodic boundary conditions. And here we are able to, for example, find the fractional quantum molecule crystallize as we increase the fraction strands and increase on level mixing. So you're absolutely right that whenever we do with finite size, we have to think about minimizing the finite size effect.
That's all we have time for, so let's take a speaker again.
Yeah. Oh, sorry. This pi does not mean the 3.1 network. Just the foundation.
Is this the next one? That's all I get. Put it there.
If it's red on the side, you should push the button.
Okay, now it's a microphone. And it works?
Yeah.
All right, great.
Great. So the next speaker is Matt Otten, and he's going to tell us about quantum simulation and chemistry and materials.
Great. Thanks, everyone. Thanks to the organizers for having this great workshop. Very happy to be here. I'm not the only one from Wisconsin. I brought a bunch of my friends and group members, and so talk to them as well. They'll have posters. Today, I want to talk about the places quantum will go towards useful quantum simulations in chemistry and materials. And so first, I have this whimsical map that's inspired by Dr. Seuss. I have small children. I read Dr. Seuss books. But also quantum mechanics is sometimes feels whimsical and fantastical. And so I think the theme fits. Here I'm going to define 3 destinations for useful quantum simulation. These are 3 problems that are grand challenge problems, but they also come from the literature of here's what we would do if quantum computers were a thing. This is why we need to build quantum computers. One is the rusty coast. Corrosion causes materials to fail. And this is an enormous cost to industry, to ourselves, to the army. The rust sort of affects infrastructure and vehicles at quite enormous cost. There's a lot of carbon in the air due to burning fossil fuels. That's sort of bad. It causes problems in climate, and it would be great if we can get rid of that somehow. Pumping less carbon in the air is a great solution. That doesn't take the carbon dioxide out of the air. And so in the carbon capture crags, we might be able to design a catalyst which takes carbon dioxide from the atmosphere and turns it into something else. Maybe that is a fuel that one could then use to instead of taking new fuel out of the ground, or maybe you turn it into a carbon nanotube and you bury it, and now it's gone. And finally, we have the nitrogen valley. Fertilizer feeds the world. The Haber-Bosch process is what we use to make a lot of fertilizer, and it takes around 3% of the global energy. It would be great if we could figure out how to do that in a much more cost-efficient manner. So these are three kind of grand challenge problems that we hope we could tackle and solve with predictive chemistry and material science. However, there's this problem that a previous speaker brought up, great, is this strongly correlated electrons, this swirling, whirling vortex of quantum mechanics of electrons interacting with each other makes it really, really hard to do this predictively on classical computers. If we want to turn this from science into chemical engineering or materials engineering, it needs to be predictive and trusted and fast. And so we need quantitative accuracy for predictive chemistry. And classical methods can be spectacular. We saw in the previous talk about neural-based methods. But naively, the key here is naively, the cost grows exponentially. Quantum algorithms, without justification at this point, quantum algorithms can potentially save us. Quantum computers are quantum mechanical. They can simulate quantum systems efficiently and effectively under some mild assumptions. They could potentially save us, but really it comes down to the cost of building these devices and the overheads that are associated with things like error correction. And so the question for these grand challenge problems is, what are we actually trying to solve? Not just save the world with catalysts, but what is the actual problem? What algorithms, whether they're classical or quantum, are we going to use to try to solve them? And at the end of the day, what is the cost of running that? And if the classical method is accurate and cheaper, then classical methods are great. If the quantum method is better and cheaper, then quantum methods are great. And so to bring it down to the computational task, we want to simulate quantum matter. We want to predict energies and energy differences of electrons in materials and molecules. Here is an example of a magnesium-rich alloy for an anti-corrosive coating with a bunch of water molecules on top. This is something you might try to simulate if you were thinking about modeling corrosion and trying to develop anti-corrosive coatings. There are a lot of atoms here. All the atoms have a lot of electrons. It'd be very, very hard to simulate all of those. So we're not going to try to simulate everything, but we still want predictive chemistry. There are two platforms that I'm mainly going to talk about in this talk. Classical algorithms. There's a laundry list of them. I'm not going to define all of them, but they go from exponentially scaling full configuration interaction, which is guaranteed to be exact, polynomially scaling density functional theory and coupled cluster, which have approximations that you can't tune directly, and then selected CI and tensor networks, which have something like a bond dimension or an expansion coefficient where you can get more accurate if you're willing to spend more compute resources. And on the quantum side, there are lots of algorithms, but I sort of just here put them into two families. There's the NISQ style algorithms that might be variational quantum eigensolver or quantum subspace diagonalization. Those are things people try to run on devices we have today, often without error correction. And on the other side, we have fault tolerant algorithms, which for all, from what we understand, is really going to require error correction because of the gate depths in those. So that's quantum phase estimation, for example. Where is quantum hardware? This is a horizons of quantum computing talk. Today we have NISQ, noisy intermediate scale quantum. There you can do limited depth, maybe 1,000 gates. And one can do impressive demos. Hey, look, we took a quantum computer of 100 qubits, we attached it next to a supercomputer, we ran some big calculation. But these, to me, as far as I've seen, and as I'll talk later, have mostly been demos. They haven't actually been doing predictive chemistry or predictive material science to help us understand. And it's very hard to reach and verify the type of accuracy from these methods that would be necessary to tackle these really large problems. On the other side, we have fault-tolerant systems. These are expensive because we have to do error correction. Every noisy physical qubit, which maybe we could get to 10 to the minus 4 on a future hardware, where today we're kind of between -2 and -3. That's not enough to do the millions or billions of gates that would be necessary. And so we have to do error correction, which we're going to call fault tolerance here. So, and there's some regime here where we go from NISQ today. Maybe hardware can get better with some more developments and the experiments. It turns out, as we'll see later, that most careful accounting of these problems, like simulating iron molybdenum cofactor for nitrogen fixation or factoring prime numbers using Shor's algorithm, need 1 billion or more gates. So that's way over here. So we need to have full error correction that takes us from, say, a -4 physical error to approximately -9 logical gate error. In the middle, we have a sort of big span of error ranges where we can do error correction, but it's not getting us to those sort of formal error, formally required error rates like 10 to the -9. That can be called the early fault tolerant regime. That's in the middle, where my personal expectation is we're going to do really, really exciting stuff there, but we don't really know what it is yet. And so part of the mission of algorithms designers like me is to think about what you could do with 1 million gates and how you would try and solve that. So that's two regimes, NISQ and fault tolerant. Where do current quantum results sit? What is the sort of state of one, at least some subset of the state of the arts for NISQ type algorithms? For chemistry, for accuracy in chemistry, today's best classical algorithms still sort of vastly outperform NISQ hardware. Our group, we have an algorithm called TrimCI, which if you want to hear more about it, Hal is here, and it's got a poster, we'll talk about it. Required about 5 CPU hours on a commodity laptop to get this blue point. This is energy, as our last speaker told us. Slower is better. There's variational guarantees. These are determinant expansions. This blue dot is what we got variationally on a laptop. A recent NISQ demonstration using subspace quantum diagonalization, which happens to use the same sort of CI expansion, determinant-based expansion, used a 72 qubit quantum computer and 10 to the 7th CPU hours. Right? So we're 1 million times faster than that demonstration by CPU hours, and we're also about 1 million times more compact by number of determinants. Yeah.
Is this all electron calculation?
This is Fe4S4 in an active space of 36 orbitals and 54 electrons. So it's an active space, not all electrons. So 36 orbitals, 54 electrons. Okay, so it's sort of not really comparable when you look at this. We're 1 million times faster, and the classical algorithms don't stop, and so we've gone even further and had improvements, which will be posted to the archive very soon, using orbital optimization, which sort of takes our variational energy and moves it down here for only, say, 10,000 parameters. We can get 3 to 7.2, whatever that means, but that's a lot better than here, and also a lot better than what we had originally. And so that's through rotations of the orbitals, which gives us another degree of freedom and more parameters to optimize. And so from the state-of-the-art NISQ, we're sort of classical, at least in these types of problems for chemistry here. classical is still winning, and there's a lot of ways to go for quantum. What about the other side of the world, the fault-tolerant algorithms? Their progress there, costs are dropping fast. You can't run anything because you need gajillions of gates, but you can do resource estimation. You can ask exactly how many gates do I need. Full stack improvements, which include algorithms, compilation, and error correction, have allowed us to go from initial estimates, say about 9 years ago, saying it would take 1 century to do FOMOCO, the iron molybdenum cofactor, which is important, which is a part of the nitrogenase enzyme, which is important for nitrogen fixation. Our initial resource estimates said it will take 1 century to solve this problem on a quantum computer. That's far too long. However, developments over the last over 8 years brought that down to about a day or a few hours. So some flagship targets have moved from decades to hours in projection. That's great. We still don't have this here. We can't do 10 to the 9th Toffoli gates. We don't have. You have a question?
Can you tell us which chemical system or molecule or atom, what you're talking about, which real system?
Yeah, so this is
to understand.
Yeah, so this is the iron molybdenum cofactor, which is a nitrogenase enzyme, and it's specifically a subset of this big floppy biological thing.
Molecule, or what is
It's a large biological molecule. Yeah, but we're just looking at a small active region of that molecule, which has iron.
active center?
Yeah, iron, molybdenum, and some carbonine stuff.
Previous, when you said 56, what was it?
This is an iron sulfur cluster. So 4 irons, 4 sulfurs, which is similarly, so 4 Fe, 4s. It's similarly the active space around that. So just the important orbitals around it. Yeah, no, thank you. And so we've gotten down to hours and projections. We still can't do it today because we need 10 to the 9th Toffoli gates and approximately a little bit over 1 million qubits. So whereas hardware, quantum hardware is steadily progressing, it doesn't seem as rapid as the decreases in the algorithms. This work here, how to build a quantum supercomputer, sort of looked at the trajectory of specifically superconducting qubits, the style that John Martinez, these are basically all experiments John Martinez was a part of. He did early correction experiments. He did quantum supremacy. The Google team then did the surface code experiment. That trajectory is not getting us to 1 million qubits very, very fast. If we followed that, it's 2040 or something. And so there really needs to be something on the quantum hardware side that changes. Maybe that's a totally different platform, right? This is tracking the development of one platform. It doesn't include neutral atoms or trapped ions or photons. It could be a different way of building superconducting qubits, which is argued for in this work. But it's important to note that we need 1 million qubits, and we're not getting there. And so the hardware needs to speed up in their improvement. I can't fix that because I'm sort of bad at experiments. I'll break the laser. But I just really want to keep that into perspective, that I'm talking about 1 million qubit problems, and we have 100 physical qubits. Yeah.
Does this plot include any information about, like the quantum volume essentially? Obviously, if you can make 1 million qubits, but they're totally incoherent, this is not.
Yeah, this doesn't specifically, it's not rigorously saying the error rates have to go down with increasing size or anything about that. But it is sort of tracking useful milestones of what you would need. So it's not just I built 100 qubits, it's I built 100 qubits and did a surface code experiment. So it's a state-of-the-art experimental demonstration of a subroutine that we would want to use for one of these types of applications. Okay, so that's on the quantum side. I think it's good to compare with classical. So how do classical algorithm designers try to tackle FOMOCO, the iron molybdenum cofactor? Here, this work from Garnet Chan claims that he can solve this exact problem, the same one that was estimated in the previous slide. So it would say a quantum computer would take one day on a million qubits, a device that doesn't exist. Garnett from Caltech claims that using unrestricted density matrix renormalization group with 400,000 bond dimension, that's very, very large, but he could use Frontier, one of the largest supercomputers in the world, a device that does exist. It's relatively expensive, but you can go touch it. He thinks he could solve that same exact problem, precisely the same, in about one day. And so the quantum algorithms people say, I need a billion gates, I need a million qubits. It's going to take me about a day on with some architectural considerations baked in. And the classical computing people say, well, it's only going to take me one day on a device that is built today. And so it's an interesting dichotomy on the side of the NISQ processors. We don't really have any indication that they're better, and they're sort of maybe a million times worse by our accounting. And on the fault tolerant side for this application, which has motivated algorithms development for 8 years, it's not clear that that would provide a distinct or large advantage either. Question.
I think there's also a question about energy consumption of Frontier versus energy consumption of a single dilution refrigerator.
You can't fit a million qubits in a single dilution refrigerator.
Two trapped neutral atom computers.
You probably need 10 traps. You need about 10,000 to 100,000. It's a great question. This does not include energy consumption, but I think that thinking about the energy consumption of a device that's going to take another $1 billion to do R&D to even build, compared to the energy consumption of a device that exists today, when I'm thinking about trying to solve this, it's very, very hard to, I'm not an economist, I can't work out every single detail, but I do think it's important to note that Frontier exists, right? Nobody can build a million qubit computer today. Maybe in 3 years, and maybe in 3 years we can talk about energy consumption and that. I'm not saying we shouldn't build quantum computers. I think we should, but I think we should always be really cognizant of what the best state-of-the-art classical is, where the resources are for quantum, and how that motivates our design of the systems and the algorithms.
It's saying classical compute is going to require for error correction, but also you want it. The energy question is subtle because it depends on how you're doing error correction. It's a good question, but it's a subtle question because you're going to be using a lot of classical compute to do it.
Yeah, there are going to be GPUs sitting next to your QPU just churning the decoder. It's a great point. Thank you. So this is like what motivates my research, and what really, really are the questions that I try to ask is, the algorithm cost is not a runtime. We have to factor in overheads. Hardware alone doesn't just solve things. We have to really put together to find utility. It's the composition of algorithm. You have to compile it and really get something runnable and make that efficient. You need error correction almost certainly to make this work, but maybe not full. Maybe we can do early fault tolerant. And then you have to think about architectural considerations. And I do a lot of resource estimation in my work. I can't just go and build a quantum computer and test these, but I think really carefully about how the resources, what the cost is. And so before getting into the quantum resource estimation part, I just want to note that when you're thinking about an application at this level, quantum computing is not the only part. It's going to be embedded in a classical workflow. And in this work in NPJQI, in quantum computing for corrosion simulation, I worked with Boeing scientists to really understand how they try to solve their corrosion modeling problem and where we could slot in quantum computing. You don't need it for geometric optimization because DFT is good enough. Your errors and where the positions of the atoms aren't that bad. So they don't really think you would need the cost or accuracy of using a quantum computer. But for computing activation energies, that's where one would really need to have the accuracy that quantum phase estimation would allow us. And so to do these types of quantum resource estimations, we develop tools and use other open source tools within a larger workflow to really understand throughout the stack, the fault-tolerant quantum computing stack, what the full resources are. So we can go from a problem like using a ruthenium-based catalyst to turn carbon dioxide plus hydrogen into methanol and water. So this is the carbon capture problem we would want to simulate. We have this crazy ruthenium-based catalyst that you have to calculate the energy difference between state 1 of the catalytic cycle and state 13. That's sort of what we're trying to calculate here. In the stack, we are looking at various different choices that one can make. You can choose what quantum algorithms you run. You can choose the logical quantum processor and how you sort of write it down, whether it's poly-based computation or sort of lots of lattice surgery and such. You have to choose your error correcting code and how you deal with t-states. And at the bottom, you have to think about the architecture, well, as things like the speed of your measurements. All of that goes into computing something like it will take about 4 hours to compute FOMOCO on some device. Today, I'm mostly talking about algorithms. You can go see some of my students' posters in the poster section where they talk a little more about error correction in the physical quantum processor. And this is work with Katerina, who's not here today. So in this work, where we both developed the tools of this resource estimation stack, but also applied them to this ruthenium-based catalyst problem, we looked at calculating complex 13. So that's ruthenium in the middle with it's a molecule. We're looking at an active space of 56 orbitals and 64 electrons. So that's sort of far beyond what one would naively expect to be able to do on a classical computer. It takes about 112 qubits or something. We took developments in the last sort of 5 years since the original publication of this problem in the literature from Beverland et al. In the Microsoft team. They initially estimated it would take about 22 years to solve this problem on a trapped ion-like processor. We looked at the latest and greatest spectrum amplification with double factorized tensor hypercontraction algorithm. We used graph state compilation and ZX calculus to reduce the total number of gates. We implemented the resource estimations of magic state cultivation instead of distillation, which is a big win. And we used a detailed ion trap hardware model, which includes sort of networking costs. It's a modular processor. So all of those were innovations that mostly came from the literature. They were distinct papers that sort of sat in their own buckets that weren't put together. What we did is put them together in one tool so that we could say that 1, 2, 3, 4, these 4 or 5 different innovations over the years took it from 22 years of expected runtime to 1 day that we got in this work. And so that's great. But the point of sort of the tooling and the thing that I'm quite interested in is now we can do like an analysis of what the different innovations gave us. And so in this plot, we have on and off, orange is off, green is on. At the bottom, we have this highlight 1 day number. And we sort of can look at, well, what if you turned off double factorized tensor hypercontraction and left the other 3 on? That's sort of experiment 4. It would take 58 days. And so that's a 58 times reduction from using double factorized tensor hypercontraction. Or you can say, what if the algorithms people never did anything what if the algorithms people are the only people we had and the rest of the stack wasn't developed? It would be 500 days instead of sort of 57 days. So there's a lot of data here. Yes, Brian.
So this looks really nice. Is there any cost and accuracy in this approach? In terms of hypercontraction, does that actually lose you some decimal points somewhere?
It does not. You very carefully change you very carefully control the errors that could be propagated from DFTHC, such that your total error budget doesn't go above chemical accuracy.
Well, I understand you're keeping chemical accuracy. You still might be losing digits. Really like tweaked everything, so that's not the case.
Yeah, I mean, we haven't run it because we can't run it, so it's hard. But I think that the accounting is such that you shouldn't lose any accuracy. So there are a lot of insights one can make here. But we can also take this tool and go beyond just this ruthenium-based catalyst and move on to many other systems. And so here in this work with Zhang and Katerina, we looked at 1, 2, 3, 4, 5, sort of 6 different systems that exist in the literature as, hey, use quantum computers to solve this. This is from a sort of drug discovery relevant cytochrome P450, already mentioned FUMOCO, these ruthenium-based catalysts from the previous one, as well as iron sulfur clusters, which also have shown up. And you can do it, you can just run them with our selected CI, our trim CI algorithm. You get these bubbles, those are classical results. The size of the bubble is our expected accuracy. We might not know the answer, but we can sort of do self-consistent checks to figure out how accurate we are. And so for instance, FUMOCO took us about 1 billion total integrated seconds. If we do a QPU estimate, it's about 1 million integrated seconds. So there's a 3 orders of magnitude difference between that. But this is small and this is big. So they're not at the same accuracy. So FUMOCO, at least for selected CI type methods, is still, say, a candidate for quantum advantage. But this, interestingly, this ruthenium-based catalyst with 100 orbitals, which has more orbitals than FUMOCO, is actually really, really small. It runs pretty fast on our classical computer. And the gap between that and the quantum computer is actually quite small. So you probably shouldn't try to solve that on a quantum computer because your classical computer is pretty good at that. And so we're sort of doing going through all of these applications to really understand the boundary of quantum advantage using our best state-of-the-art classical and comparing to these kind of state-of-the-art quantum resource estimates. And I only have like 1 minute left, so I'll just flash. I don't think quantum computing is dead, and what I'm really interested in is figuring out how to utilize our knowledge of classical compute, that we can get really, really good answers on classical computers, and use that to feed the quantum computers so that they're faster. And so this work looks at loading a trim CI or selected CI wave function into a quantum computer for the initial state so that we can actually lower the total runtime in that estimation. And so if we load about 1 million determinants, we increase our initial state overlap, and our runtime goes down by a factor of 3, but we actually don't want to load 1 billion determinants because the runtime starts to go up. So we can use our classical algorithms to feed the quantum phase estimation like algorithms and hopefully do better. And Jiang will be able to tell you about Canoe in her poster if you want to go see that. So where do we go from here? Well, we have this whirling, twirling tornado of electron correlation. What do we do with it? Well, I think we need more applications. FUMOCO doesn't get us there. We can't use FUMOCO as the reason to build a quantum computer anymore. So more high utility applications, the more routes we'll have so that we won't necessarily block one. I think early fault tolerant algorithms are really, really exciting, and we need to think about how to reason about these heuristic algorithms and these very powerful devices that will be coming online in the next few years. They won't have enough qubits for the full DFTHC QPE, but they'll be really exciting. And we should co-design with hardware. We should really think carefully about what the hardware can do so we can minimize some of those overheads that go into these resource estimates. So thank you, everybody. Many of these people are here from a group. Feel free to talk with them, and I'm open for any questions. One minute over. Yes.
Maybe this is a little bit tangential, but I mean, you mentioned quantum phase estimation and resource estimate. So it always confuses me because you need an initial state and you can never get an initial state. So
that's exactly what this work is about.
Yeah. Okay.
We're using our initial state from our best classical algorithm, and we're computing an expected overlap with the true ground state, which allows us to compute the overhead of that.
Right. But in principle, if one talks about exponential quantum advantage, that could never work, right? Because if I increase the size of the molecule, that overlap is always going to scale exponentially.
Yeah, so this is a subtle argument, the Van Vleck catastrophe. In practice, which is what I'm sort of a little more practical, we're really good at thinking about pretty good states. We're just bad at getting to perfect states. And so I think my intuition, which is not supported by hard theory, is that we're almost always going to be able to find an initial state with sufficient overlaps that we won't fall into that catastrophic regime. But I can't fight the theorems.
But okay, so maybe a follow-up is maybe more optimistic follow-up is it seems unlikely that we really need that accuracy and overlap because there is finite temperature. So is there an algorithm that takes that into account that, that there is anyway some finite temperature?
So if you're thinking about the fact that we want to solve systems at finite temperatures, it's a great question how to actually include that. These are all at 0 temperature, and it doesn't seem to be a catastrophe here. Maybe it's easier, but then you have to get into like give state preparation, which is itself is a bit hard.
Yeah, maybe first a quick relate to your question.
Yeah.
So even though the overlap always decays to 0 in the large system size limit, physical observables, right, such as the energy density,
Sure.
Such as the energy gap, but that does not necessarily decay.
Oh yeah, absolutely. But I think that important for the quantum phase estimation, if you don't have the question is what happens if you run quantum phase estimation with a wave function that has like a 0 overlap, then it will take exponentially long time to converge.
Oh, so you're saying that
I think that's a problem. Yeah.
It's related to my next question, which is could you describe a little bit more like how these how quantum errors, all right, in the actual hardware may affect some of these quantum calculations?
Yeah, I mean, we tend to just fix quantum errors with quantum error correction. And so the errors of a bit flip or a phase flip are naturally just dealt with error correcting codes. And what that means for the resource estimation is based on your error rate, what is the overhead necessary to get rid of that scale. So if you have a better qubit, you have to do less error correction. So, being sub-threshold is the terminology the jargon we like to use. Being right below threshold means that you could just concatenate your code sufficient or make your surface code large and use a lot of resources. But if you're a lot below threshold, the overheads are less. And so we want to make the qubits better, but as long as we're sub-threshold sufficiently, it just becomes an accounting number in the total resource estimation. Good.
Thank the speaker again.
Yeah, I think that the
So I'm curious about your.
Yeah, soon.
Your definition of sorry.
Yeah,
Really indirect.
I think we need different algorithms that are beyond this fault tolerance. My student Jiang has a poster about one. And I think if we don't work forward our best classical now, unfortunately, it's a part of the summer.
Okay, we're going to get started. Really happy to have my colleague Zhang from Chicago.
Hello, everyone. With pleasure. To have this opportunity to talk about some of the stuff.
Yeah, can you speak up?
Yeah, audio I need to wear.
You need a microphone right there.
Well. Should I just vote?
Gotta click.
That way?
Gotta click. So
Okay. Oh,
I put in the drawer.
all right. Can people hear me better?
Yeah.
Yeah. All right. So today I'm going to talk about like entanglement in learning, and this is it's actually a large collaboration with both the theory from Chicago, Argonne, and Caltech, and also experiments from IBM and also like Denmark. So I think that maybe for this audience, people might have already heard about like a lot about like a quantum advantage using like either qubit systems or could be quantum advantage using these like bosonic systems. And on the theory side, like ideally we know like, okay, if there's no decoherence actually in the qubit systems, like it's very likely we'll have like a really like exponential quantum advantage. But in the presence of noise, actually like maybe we will only have like some polynomial scaling. On the other hand, if it's a bosonic system, it's even more ambiguous because earlier people demonstrate like with a few hundred modes, with 300 photons, and they claimed it will take like millions of years to do it. But recently, collaboration with Beckman, we find that we actually, because the system for the bosonic system is actually pretty lossy with only 50% transmission, then it doesn't matter how much squeezing you put in the end, it's no more than 3 dB squeezing a mode. So that's kind of like a significantly reduce the amount of entanglement in the systems. And we actually take advantage of the noise to develop efficient algorithm to simulate like 100 of modes both. And that's kind of like what happened 2 years ago. And just yesterday, there's a Nature paper published from Jiang Pan's group. They actually significantly extend the number of modes to a few thousand modes, a factor of 2 or 100 more, so that the entanglement does increase. And kind of it's still open question whether or not there exists like an efficient classical algorithm to simulate such a system. So you may notice that there's this back and forth of kind of like a quantum hardware improvement, improve the classical algorithm, then another further improvement to quantum hardware to address these different challenges. So this is kind of like definitely like, okay, it's good for both sides. But on the other hand, we'll also be interested in the following question, that are there other quantum advantages that hopefully it's provable and we know where the boundary is between classical and quantum, and it's robust in the presence of noise, and hopefully it will also be useful, that we can use such a thing to do something useful. And the setting is actually like related to the quantum learning. So here is like rather than just solve like an NP problem, it's actually like try to learn another aspect or try to learn about like a quantum system, which has many like features we'd like to learn about it. And for example, like pioneered by like Robert Huang, John Pascal, and Jerry McLean and others, they actually like find that there is a quantum advantage if you actually directly learn like using the quantum states from the experiment, right? And it's kind of along a similar line, like, okay, sometimes it's better we directly like access the quantum resource rather than do a projective measurement and then use the classical data and try to learn about the quantum system. So now here the question, like the important one is actually in order to have an advantage, we should have some pretty unique quantum resources that would enable us to achieve such an advantage. And we know like, okay, some of the resources like quantum entanglement could play a very important role in such a quantum learning tasks. And in today's talk, I'm going to highlight that it is true that entanglement is crucial, that we can differentiate whether the scheme uses entanglement or not using entanglement,
will lead to a separation that whether or not we will have a provable quantum advantage. And here, in order to be more quantitative, to say, okay, what advantage we have, we're focusing on the sample complexity, which is how many rounds of experiments that you need to do, or how much like quantum data you need to collect in order to learn about such a quantum system. Because we know in reality, like the quantum experiments takes time. And if we, for example, if you want to learn about the quantum system, if it take like hundreds of years, then probably that's not a very efficient way to learn about it. So practically, we do care about the sample complexity. So, and we would like to see whether the sample complexity grow polynomially or exponentially with the system size. So now I'm going to talk about like this entanglement enhanced learning. The short name is EO. Hope it's easy to remember. And let me start with the simplest task. Suppose I have a single qubit poly gate. It could be identity, X, Y, or Z. So there are 4 poly gates acting on a single qubit, but we don't know which poly gate is applied. And suppose I only have 1 qubit. I only have like, I can query input like 1 qubit at a time. Then I need like 2 queries, because we can put in 0, see whether the bits get flipped. We can put a plus, whether see there's a phase flip or not. Because each measurement only gives us 1 bit of information, so we need 2 classical bits of information to differentiate 4 possibilities. On the other hand, if we have entanglement, we actually can do it with a single query. The idea is simply putting a Bell state, 0, 0 plus 1, 1, and then the output will be 4 possible Bell states, each of which associated with exactly one of the poly gates that are being applied. So there's a 1-to-1 correspondence of output of the Bell states correspond to the poly gates. And it's entanglement that effectively expand the Hilbert space that allow us to unambiguously distinguish these different poly gates. And in this case, we only need a single query to learn about this poly gate. And for people familiar with quantum information, this is another way of saying quantum superdense coding. So now the question is, this is a factor of 2 advantage for single qubit channel. What if we have n qubits? Do we get a 2n or we get 2 to the n? Right, that's a big difference. And so in order to like further extend, we actually would like to introduce differentiate different type of learning tasks. One of the learning tasks is called entanglement-free learning, that we basically just put in the states without additional entanglement with additional reference systems. And the second type is entanglement enhanced. We have additional ancilla that entangled with our probe, and later we'll measure both the probe and the answer. Yes?
Sorry, just from this simple example, it seems like what you get from queries, you somehow lose with sample complexity. But that would be the case there too.
Yeah, we can reduce the sample complexity by factor 2 for that simple example. Yeah, and the question is, when I have n qubit poly channel, what's the reduction of sample complexity?
Oh, but what I mean the sample complexity is not the query complexity, but when you need to measure the Bell pair, you need 2 measurements.
Good. Excellent question. So effectively, we can say it's a query complexity, and the sample complexity will be even more, right? Maybe each query you can repeatedly use like a multiple. You can use multiple channels within like each query. Yeah. So then the sample complexity could be lower bounded by the query complexity. But later we'll see that actually like the optimum scheme we have, they are the same. And it's similar to kind of the scheme we have. But on the other hand, we also, if we wait for another few more slides, we'll also include the adaptive scheme as an entanglement-free scheme. Yeah. So now let's actually like, in order to maybe give a more general setting, rather than just a unitary poly gates, we actually can consider like a poly channel as a mixture of different poly gates. As we know, like in the real systems, there's decoherence going on, and we actually can do polytoiling, convert any generic noise channel into a poly channel. And for a single qubit, we have 4 poly error probabilities, which add up to 1. And the equivalent representation is this poly eigenvalues. We notice that the poly channel, if you're putting a poly operator into poly channel, the output is the same poly operator. The prefactor is a number which magnitude is no larger than 1. And the simple reason is the poly operator is either commute or anti-commute. So when you basically like determine on the commit, whether commute or anti-commute, you will have a plus or minus sign when you add up these Pauli error probability to give up the Pauli eigenvalues. So notice that if you know Pauli error probability, you can revert to figure out the Pauli channel. And if you know the Pauli channel, you know the Pauli error probability. So these two are equivalent representations. And these Pauli eigenvalues is actually, you can think intuitively, if I have a qubit, which you can represent as a block vector in the block sphere, and when it undergo a Pauli channel, then the block vector XYZ component will be reduced proportional to the Pauli eigenvalue. And the Pauli eigenvalue associated with identity is always equal to 1. So therefore, that says the total probability is preserved, but so the XYZ component is shrink depending on the Pauli eigenvalue. Okay, so now we can generalize this to n qubit. If we have n qubit, then you will have 4 to the n different possible Pauli operators. So you can imagine it's a huge space. And on the other hand, mathematically, we can similarly define the Pauli eigenvalues. And the Pauli eigenvalue and the Pauli error probabilities are connected by this Wash-Hartman transformation. Okay, you can think it as a binary version for the Fourier transform. And it's reversible, so if you know one, you can obtain the other. Okay, so with this setting, you've noticed that this is actually a very challenging learning task. We have 4 to the n different parameters you need to learn. Okay, and can we learn it efficiently? And also another motivation is the Pauli channels that I mentioned earlier. Like practically, it's including those dephasing, depolarization, and the qubit flip channels. And also for generic channels, we can use the random compiling by do Pauli twirling, convert any noise channel into a Pauli noise channel. And by learning these Pauli noise channels, we can also advance like using this information for error mitigation or co-designed quantum error correction. Okay, so now here we know like we only have a finite number of samples. We're not going to learn everything perfect. So we should set a goal that to learn the Pauli eigenvalues with epsilon precision, which by definition is the largest deviations of the Pauli eigenvalue is no larger than epsilon. And that is the goal with the finite number of samples we want to learn. Okay, so here is the result, which consists of 2 parts. The first part is that there exists a n-qubit entanglement enhanced learning protocol to learn about these Pauli eigenvalues with epsilon precision with a success probability of 1 minus delta that only uses like almost like a polynomial overhead of samples, which here the polynomial is linear with the number of qubit of the channel. And there's a sum like 1 over epsilon squared and the log of delta. And that kind of like it's a very favorable scaling because the n is actually like, okay, even when we have 100 qubits, this n of a factor of 100 is reasonable to take. Okay. On the other hand, if we do not have entanglement, the sample overhead will scale at least 2 to the n, which is exponential overhead to learn. Okay. So the special case with n equal to 1, we know it's a factor of 2. But here, actually, it can, when you n qubit, we show it will go 2 to the n. Yes.
For a generic Pauli channel on n qubits, should I expect that these eigenvalues lambda are exponentially small in the system size?
Yes, it can be very small.
So should I want to take epsilon also to be exponentially small in n?
Well, epsilon is a constant. I get. Yeah.
Right. But if I want to get a useful bound for a bunch
Yes.
of parameters that are exponentially small.
Yes. So let's be realistic. Like if the Pauli eigenvalues are 2 to the minus n, then we would not expect to learn them to that precision with the polynomial number of samples. Yeah. But sometimes there are channels later we'll see like just one of the Pauli eigenvalue is big, but you don't know which one. But this method will allow you to learn it.
Thanks.
Yeah. So just to get a intuition about like how can we construct such an efficient learning scheme with entanglement enhanced learning, the construction is actually pretty simple. We have n qubit channel. What we do is prepare n Bell pairs. And each Bell pair will contribute to 1 qubit to probe the channel. And then after that procedure, we'll actually like measure the Bell pair in the Bell basis. So each Bell pair will give us 4 possible outcomes. And with n Bell pairs, we'll get 4 to the n different outcomes. And each outcome corresponds exactly to the 4 to the n, 1 out of 4 to the n different Pauli operators it can be applied. So essentially, we'll directly sample the Pauli error of this channel. based on the statistics of the Bell pair measurement. And we can formally, because of this one-to-one correspondence, and we can formally construct this unbiased estimator of the Pauli eigenvalue as a weighted sum of those statistics outcomes. And by doing that, we actually can show that with the sample complexity that scale only linearly with n, with some additional constants, that we can actually learn the channel. Okay, so why it's linear with n? It's because altogether we have 4 to the n different Paulis. And each Pauli eigenvalue, there's a small probability delta that may fail, right? And we want to bound the total failure probability to be less than some effect total delta. So the individual Pauli should have a failure error, which is total delta divided by 4 to the n. And when you take a log of that delta over 4 to the n, you take a log, you will get a linear factor of n. And that's where this linear sample overhead comes from. Okay, so now the second part is that any entanglement-free scheme, you will have this overhead of 2 to the n. One intuitive way to show it is that basically, if you do not have entanglement, if you just use the qubits, every time you only get a 4 to the n or 2 to the n outcome. But the original distribution had a 4 to the n possible outcomes. So you're only getting the marginal distribution, and you want to infer the original distribution, which is a very difficult problem for a typical non-trivial distribution. So therefore, you will have this extra 2 to the n overhead to learn the original distribution based on the marginal distribution. Okay, but this is the intuitive proof, and the formal proof, you actually need to look into the total variational distance of those distributions, and you can bound that the information you can gain about that is only will be suppressed by the factor of 2 to the minus n. Okay, it's detailed in these papers. But related to the earlier question about the channel, I only give a very simple case in terms of no ancillor at all. So that's definitely entanglement free. But sometimes we can have classical ancillor, which help us to do some adaptive learning scheme. Or we can even have some quantum ancillor, but not entangled with your probe. And for all these schemes, which we call entanglement-free scheme. And we can show that for all these entanglement-free schemes, there is this overhead of 2 to the n. So basically, this shows that there's a clear boundary. Whether or not we have entanglement with this ancillor will determine whether or not we will have this extra 2 to the n overhead factor. Okay, so this is all ideal case, because so far there is no additional decoherence or imperfections of these tasks. And one question would be, okay, what about the practical imperfections? For example, in our circuits, we may have initialization error or measurement error, and we will also have gate errors, and maybe the ancillor idling may also have ancillor errors. So more specifically, we can look at the circuits. Generically, we will have potential crosstalks between your system and ancillor, and maybe there will be state preparation and measurement error, like a spam error, and also ancillor idling errors. So for these different errors, actually one can have different methods to suppress them. For crosstalks, we can use a dynamical decoupling because it's a unitary operation, and if you can get effective time reversal, we can decouple them. And for spam errors, actually they are spam error-free estimation schemes. For example, you increase the number of cycles of these gates and do a fit of the decay, you will know the error rates without relying independent of the spam error. And for ancillor idling error, we actually can do error mitigation because we can do Clifford toiling of the ancillor, so it will become effective like a depolarization error. And we can efficiently learn about ancillor error and even mitigate them. And notice that for spam error and error mitigation, there will be some extra cost we need. Because for people familiar with error mitigation, there is a weak exponential overhead associated with the errors you want to mitigate. Right? Simple way to think of it is if we have erasure error, to compensate those erasures, you will have this exponential overhead. So based on that, we actually need to modify those statements in the presence of noise. And the modification is actually this factor of 1 plus 2 gamma to the n, where this gamma characterizes the spam error and the idling error of the ancillor. And you may notice that, okay, this is a weak exponential. And in order to claim that we have a quantum advantage, we require this 1 plus 2 gamma to the power n is smaller than 2 to the n. Or effectively, what we need is just that this gamma is no larger than 50%. Okay, I think nowadays, many physical platforms can claim their error on individual qubits is less than 50%. So in that sense, actually, like many physical platforms, we can use such a method to demonstrate there's still a separation between entanglement-free or entanglement-enhanced schemes. Okay, so now let's actually look at like how we use such a scheme. And actually, my former postdoc, Oliver Saif, like joined IBM. Actually, we're using the IBM device to demonstrate such like an advantage. So the first experiment is the task of hypothesis testing. Suppose I have like two types of channels. The first channel is a fully depolarization channel. Doesn't matter which state you put in, it becomes a maximum mixed state. The second channel, second type is actually a partially depolarization channel. It depolarizes all the Pauli eigenvectors, Pauli like components, except one, but you don't know which one. So it's one out of the 4 to the n different Pauli components being not depolarized, but you don't know which one. So if you're giving these two channels, you actually don't know which one is, and it's very difficult to infer which of the 4 to the n Pauli is that kind of not being depolarized. And if you don't have that information, it's very difficult to tell apart between these two channels. On the other hand, if you have entanglement, you can just put the Bell states, and the Bell measurement outcome will give you a sample statistics that's associated with that particular Pauli. There is a corresponding Bell state, and that will have a high peak in its distribution. So with a small number of samples, you will know that, oh yeah, there is a peak distribution associated with your Bell measurement outcome, and you will be able to tell it's a second channel, not the first one. Okay, so this is kind of like how Bob would be able to tell the difference between the two channels if he had entanglement. Otherwise, it's very difficult. So experimentally, basically like, okay, we actually pretend there are two possible scenarios, and you'll find that those Pauli eigenvalues have a very different distributions. In one case, which is the green correspond to fully depolarization channel, all the eigenvalues are close to 0, while the case with the orange color, actually some of the Pauli eigenvalues gives a non-trivial distribution, significant deviates from 0. And as we increase the system size in terms of number of qubits of the Pauli channel, the success probability to differentiate those two things, we'll find that there's a difference behavior. So the black dot data points are the entanglement enhanced learning scheme. In the experiment, we see that even we approach to up to 30 plus qubits and channels, we will still be able to differentiate between these two schemes. On the other hand, this like the continuous curve with the blue curve, that's actually the classical bound associated with the success probability without the entanglement. And you will see like once it's above 25 qubits, then the entanglement-free scheme sort of will not be able to distinguish between these two cases, while the entanglement-enhanced scheme, you can still have a very high confidence that it's actually to differentiate between these two channels. Okay, so this, yes?
The dumb question, yeah. So here, this learning, what is the task?
The task is differentiate whether it's a green channel or whether it's orange channel. The green channel is a fully depolarization. The orange channel is almost depolarizing everything except one particular Pauli component.
It's learning different quantum channels.
Differentiate different channels. Just the bandwidth.
Yeah, because do you get information about which qubit is not depolarized?
Yes, later, based on the Bell measurement outcome, there will be a peak distribution associated with the particular Bell measurement, and there's a one-to-one correspondence of the Bell measurement and the Pauli that's being preserved. Yeah, so you actually do that. Yes.
Is there any optimization on the input to design the optimal input?
Yeah, for this task, we actually, okay, that's a good question. Here, we actually just put the simple tensor product of Bell pairs, which is experimentally easier. But maybe for other channels, you want to differentiate. For example, it could be not a Pauli, but Pauli under some unitary rotation. Then maybe it will be better designed if we put in a state, not just a simple tensor product, but the tensor product are followed by some on-rotation, right, before the rotation is done. Yeah.
So is this a provably quantum advantage?
Yes. Oh. And put another way, there's no way to try all possible entanglement-free schemes. And that's why we need actually most of the work on the theory side is to prove this bound of success rate.
Is it exponential?
Yeah, the later part, once you go larger number, it will decay exponentially. Or it will be exponentially approaching 1/2, which is unbiased. You don't know what the outcome will be. Yeah.
Compared to classical methods, is this exponential advantage, quantum advantage, or is it?
Yeah, you can say that the success probability will, how to say, classically you will have exponential success probability to differentiate them, but quantum entanglement enhanced scheme, you can differentiate them. Yeah. So this is like a binary decision, you know, which is one of the channels. On the other hand, you also want to do some more quantitative estimate about the channel. For example, learn about the Pauli eigenvalues. And in this case, we can also do it with like an entanglement enhanced learning of the Pauli eigenvalue, but it's important we need to mitigate the errors associated with the state preparation measurement, as well as ancillary idling errors. So here on the left panel, the horizontal axis is the brute force learning of those Pauli eigenvalues. The vertical axis is the entanglement enhanced learning. And you will see like the light blue dots correspond to, we didn't do any mitigation. And we see that there is a systematic bias of underestimate the Pauli eigenvalues if we do entanglement enhanced learning. On the other hand, once we do the mitigation, you see that all the data points fall along the 45-degree line, indicating that there is a good agreement between brute force learning and entanglement enhanced learning. Moreover, in terms of sample overhead, if you look at the right panel, the horizontal axis is Pauli weight, the vertical axis is actually the sample overhead. This around this like a black solid curve is 2 to the W, which is the exponential overhead, it's a lower bound of the sample overhead for entanglement-free scheme. While here, these blue data points indicate that we can actually go below that with entanglement enhanced learning. So it shows that there is a sample advantage that we can achieve. So now let me actually, in the last 5 minutes, I'll talk about another extension. We can go from discrete variable to continuous variable. And this is actually like the idea, like kind of like, okay, like once we have this discrete variable and Jean Pascal come say, oh, well, maybe we can extend to continuous variable schemes. And because they are very similar. Here is a table just to list like the correspondence between discrete and continuous variable. So the left column is a qubit, which you can see like you have Pauli operator, Pauli channels, and for continuous variable, it corresponds to displacement channel and the displacement and the random displacement channel. And for qubit, you have Bell state, and for continuous variable, you have two-mode squeeze state or the EPR state associated with the infinite squeezing. And you can do Bell measurement for qubits and similarly Bell measurement for continuous variable, which is the sum of the position difference of the momentum. And the Pauli distribution corresponds to random displacement distribution. And the Pauli eigenvalue corresponds to the characteristic function, which is the Fourier transform of the continuous variable displacement. So here is like a single mode like advantage. On the left-hand side, you try to learn about the displacement with a 10 by 10 grid with 100 displacements. And if you just inject in the vacuum state and do something called the heterodyne measurement, actually we know like from Heisenberg uncertainty principle, when you measure position and momentum, there is an uncertainty associated with the product of the position and momentum. And here, like we let them to be equal because we just inject like a vacuum. And you will see these blocks, which is associated with the 1 sigma uncertainty due to the vacuum fluctuation noise. On the other hand, if we have entanglement, what we can inject is, ideally, you can simply inject EPR states, which is the eigenstate, co-eigenstate of sum of the position and difference of momentum. And after like one of the modes going through this displacement channel, you can perform a Bell measurement, which is the sum of the position and difference of the momentum. Because these two operators commute with each other, you can actually measure them with arbitrary precision. And compare with the initial knowledge of the sum of the position and difference of momentum, you'll be able to estimate what's the change of the position and the momentum which is acted on the first channel. There's no constraint about how precise we can measure the change of the position and momentum, because the Heisenberg uncertainty principle only says you measure the position and the momentum, but didn't say about measurement of the change of the position and the momentum. And this is the explicit way to go beyond that constraint. And we can, then ultimately the precision is limited by the amount of squeezing that we have to start with. And here is the 4 dB squeezing. We can show there is such an improvement. And now if you go to the n qubit or n modes channel, then if you entanglement free, you will be limited by the vacuum fluctuation noise. and there will only like sample distribution will be smeared out due to the vacuum fluctuation. On the other hand, if you have two-mode squeezing, then you are not limited by vacuum fluctuation, and we can directly sample the distribution, only limited by the amount of squeezing we have. Okay, so intuitively, you can think that, okay, we have a M mode, and each mode will have position and momentum, so it's altogether, it's a 2M dimensional probability distribution associated with the random displacement channel, and which is characterized by the distribution P alpha. And we can consider a characteristic function, which is the Fourier transform of this 2M distribution. So if there's some like periodic structure associated with those distribution in the position, momentum, displacement, then in the Fourier transform, there will be some peaked behavior to characterize those modulations. Okay, and once we know, similar to like polychannel with the poly eigenvalue, we can recover the channel. Here, if we know the characteristic function, we can also recover the channel. So basically, they are equivalent representation. So ideally, okay, we can, with both of these, characterize the system. And in the presence of like, in the absence of entanglement, in order to learn the distribution will be smeared out by the vacuum fluctuation noise. So therefore, the peak behaviors will be smeared out. And if you look at the characteristic function in the Fourier domain, then those oscillation peaks, the peaks associated with oscillations will also be smeared out. It becomes difficult, you start losing information. On the other hand, if you have entanglement, you can almost fully recover the original distribution because the spread is much smaller than the features you want to learn. And in the Fourier domain, you can see the characteristic functions are almost fully preserved. Okay, so one can be a bit more quantitative in terms of like what's the overhead in terms of sample overhead. And you will see that actually it will grow exponentially as the system size gets bigger. Okay, so let me actually like get to the claim of the results is that if we have entanglement enhanced scheme, because we have only finite squeezing, you can think the squeezing is kind of the additional noise that you added in. So you will be having this weak exponential overhead factor of the exponential to the e to the minus 2 gamma times the beta. Okay, and this gamma, this R is actually the squeezing that you have. If you have very big squeezing, then it will be essentially exponential to the 0. Okay, and on the other hand, if you do not have squeezing, then there is some like effective dimension of associated with this information you want to learn. You'll go that effective dimension to the power n. So that will be another exponential overhead. And experimentally, we actually collaborated with Ulrich Andersen's group at Denmark. We actually find that as you increase the number of modes, the sample overhead will increase. And this black dashed line, which increases exponentially with the number of modes that you have, is a fundamental limit about like the number of samples you need for entanglement-free scheme. And if we have squeezing, we actually find this about 5 dB squeezing, you can go well below this fundamental limit. And compared to this traditional heterodyne scheme, which is above that limit of the entanglement-free scheme, there's a factor of like 10 to the 10 advantage. And compared to the fundamental limit, there's a factor of 10 to the 5 advantage. And different from the earlier schemes, this is actually a provable advantage because we know that fundamental limit is actually like it's not based on some conjecture. This is actually something like you can prove.
Yeah. So on your previous slide, in the absence of noise, the cost was independent of n?
Yeah, so here like the noise is intrinsically embedded in the question as a finite squeezing. And ideally, if you want to think of the noise-free case, is just to say squeezing in the infinity. And if the squeezing in the infinity, e to the minus 2r is 0, so this factor is gone, then you will not have that overhead.
Okay, but you're saying that I guess on the experimental plot, right, you have an exponential in n, and you're saying that exponential is actually in this first term.
Exactly, that exponential is due to the finite squeezing. And here you will see that you can think that the heterodyne is a 0 squeezing. And this green curve is about 2 dB squeezing, and this cyan curve is about 5 dB squeezing. Yeah, so we see as you increase the squeezing, you actually can go below that threshold. And on the lower left corner, you also show like with the same number of samples that you increase the squeezing, you can learn more and more features associated with this characteristic function, which is like a triple peaked characteristic function. Okay, as another like a test, I know I'm running out of time, is that if you can also do this for hypothesis testing. suppose you have two channels. One is a typical Gaussian channel, the other is a multiple peaked like a displacement channel. You will find that if you do not have squeezing, this is actually the distribution becomes like a significant overlapping. As you increase the squeezing to 2.5 or 5 dB squeezing, you will see that actually the distribution become very well separated. So you can fully accomplish this hypothesis testing tasks. Okay, so just as a summary, I kind of point out like there is a distinction between like entanglement enhanced learning or entanglement free learning for both discrete and continuous variable systems. And as an outlook, it will be actually like think about what will be the applications for such like a polychannel learning or CV channel learning. Because we already showed that it could be useful for benchmarking systems or potentially used for error mitigation for more complicated channels. But it'll be good to see what other signals we can learn for these entanglement enhanced learning. And it's also on the theory side, it'll also be interesting to see like, okay, what other channels we can learn besides polychannels or displacement channel, and also what's the relation between quantum learning and quantum metrology. Because quantum learning can kind of think of as a multi-parameter estimation. And metrology, there's a quantum feature information. And in some of the recent work we show there is some connection between these two things. And another fundamental question is, what other quantum resources would enable us to achieve like a quantum advantage in terms of quantum learning? Okay, yeah. And finally, I would like to thank all my collaborators on both theory and experimental side. Thank you for your attention.
Precisely one question.
Okay, Michael, you raise a hand first.
Yeah, can you just comment on how, like, if you impose a locality on the noise model, how these results change?
Yes, a very good question. So here we assume a generic noise model, which have 4 to the n. But if you impose a locality for k local, it probably will be some like n to the power k. Then I think the advantage will not be like exponential, but probably like maybe there will be some like maybe you can reduce the polynomial overhead a little bit. And on the other hand, as you have a device, if you have no idea what's happened to the system, then probably this would be a first one to quickly get an idea about what's going on.
Let's thank Liang again.
Subjective and more you like see it in the answer. So you can measure so it sounds machine. It's a butter and service.
Good.
Now our last talk in the morning, we're going to have you, Zhang, tell us about quantum simulation of open quantum.
Yeah, thank you for the introduction and thank the organizer for the invitation. And yeah, today I want to talk about our recent work on the quantum simulation of open quantum system with a partial quantum error correction. So this is our recent idea how we can shift the noise from the quantum circuit from qubits and do some useful simulation before for total quantum computing. And in particular, actually, this can even be used for total quantum computer as well to save a quantum resource. So the main message is that actually, so you can reshape the noise and so make it useful and to remove the undesired noise channel, but keep the desired logical channel to mimic our target dissipative dynamics. Then this way, we can make it useful for open quantum simulation. This is the main message. So yeah, so in the next I will give you some more detail on how we could achieve this goal. And so I guess, from the paper talk, already know what's the challenge of current quantum computer or even for total quantum computer. The noise is the main, I would say, challenge on quantum computer. So this is quite different from classical quantum computer. Here I use one widely used NISQ quantum algorithm example, which is VQE. So I guess all people know this variation principle. So if we from the grounds, we can do some trial state with a certain parameter and minimize the cost function. As long as our wave function, so this phi theta, can cover the entire hyperspace, we can guarantee we can get the very accurate ground state. And then the VKE that so you can put this parameter rest wave function ansatz on quantum circuits and use the entangled gates to introduce the correlation. So in principle, if you start with some like, for example, like mean field reference, and if you put more and more quantum gates, in principle, if you put more gates and you can introduce more correlation, and then you can sample more ratio of hair space, and you can get more accurate result. But in practice, so if you put more and more gates, so this is double-edged sword. So you, at one time, at one side, if you put more gates, you can sample the larger subspace in over this entire hyperspace, which can introduce correlation beyond your mean field difference, and then get the result more accurate. At the other hand, so every gate is kind of noisy, particularly on this disk device. Even though on for total quantum computer, you need to use some standard qubits to correct the error. So in general, gates is noisy, and you can introduce noise. So in particular on this disk device, if you introduce gates, it will first introduce correlation to reduce the error. And on the other hand, it will introduce the noise to increase your error. So this is actually this was your expectation if you do quantum algorithm. But in practice, if you do very naive quantum algorithm, likely you will get this curve. And then you can do some improvement with shallow quantum circuits, and likely you will get this curve. So you will decrease the error to some extent with the shallow quantum circuits, and eventually if you put more and more quantum gates, the noise will be larger than your residual correlation, and then you will have this increased error in your simulation as the increasing of the gates. So that's the challenge. And this noise comes from different sources, like short finite coherent time, or control error, or measurement error, or retard error. So yeah, so that's a major challenge. And in our previous work, we have developed a different strategy, try to mitigate the effect of noise with a different technique. So one example is that we developed the so-called permutation VKE. The idea is that you want to, when you do the mapping of your physical model on the qubits, you want to your strongly correlate orbital putting them together. So in this way, you can reduce the number of gates to entangle them. So this is why we call the permutation VKE. Actually, this idea is inspired from the DMRG simulation. So for example, if you do like a DMRG simulation with the MPS, you are mapping your high-dimensional wave function into one-dimensional tensor network. And if you want to reduce the bond dimension to achieve the same accuracy, you can do some permutation on your orbital to reduce the bond dimension. So that's the idea where this permutation VKE comes from. And then you can also do another trick that you can do some clustering on your orbital and use some trick to do the partition, your graph theory, to partition your orbital to a different group. And you can minimize your intercluster correlation and maximize your intra-cluster correlation. In this way, you can further use some like an intercluster unitary to address the Hamiltonian to remove the entanglement from wave function. And you can separate the circuit into smaller quantum circuits. This is another way you can do kind of larger scale simulation on smaller quantum device, and also with shallower quantum circuits. And also we have some other method to go beyond VKE. And also, to address the best problem, we have some so-called correlated Hamiltonian approach because if you look at literature, many of this quantum simulation we are using like a minimal base set or small base set. But in practice, we need to use very large base set to converge. So anyway, so you make one overall. Actually, we are trying different technique. Try to minimize the fake noise by making the quantum circuit shallower to reduce the fake noise. But yeah, after we did all this work on the grounds and statistics and dynamics, then we think about actually can we make use of noise instead of fight with noise? Can we use noise? So this is the motivation of this work. Yeah, so in particular, yeah, we want to start with the open quantum system. So this is kind of a sweet spot where actually we can reshape the noise from qubits to mimic the distributive dynamics of open quantum system. And fundamentally, actually, all the quantum systems we are dealing with actually is open. So basically, there are always interaction between your system and your environment, and this will introduce the information and energy exchange between system and its environment, and making your system is not non-unitary dynamics, and introduce the defacing and the realization. So this is very fundamental to many different branch of physics and chemistry and materials. For example, previously I was working on the quantum transport. In quantum transport, you have a device connecting to environment that will drive your transport from coherent transport to like diffusion. And also you have like in materials, like in particular for qubits, we're designing different qubits. So one challenge is that how can to reduce the decoherence to make the coherence time longer. So, and also in chemistry, we are studying a different reaction in solvent or in different environments. That will also introduce the decoherence and the relaxation of your subsystem. So fundamentally, all the quantum systems are open. But if we want to simulate it on quantum system, actually this is very, very challenging. And fundamentally, this is very different from the closed system dynamics. For closed system, you can have this unitary dynamics, and this can be naturally mapped to the qubits. I will discuss later. And then, in contrast to this in contrast to the open closed system, for the open quantum system, we have additional terms. So this is the dissipator. So this dissipator counts for all this interaction between your system and environment, and that will cause trouble if we want to do a simulation on the quantum computer. So in particular, what's the challenge? So for example, here is how we can derive the open quantum dynamics. So you can start with some Hamiltonian for the entire system, and then you can do the dynamics of the entire system, and then trace out the environment to do filter, and then you can get the dissipator. Actually, there are different favorite ways to derive the dissipator, and one widely used example is linear Brownian dynamics. If you assume like a wiggle coupling and assume Markovan approximation, then you can get this widely used dissipator. This is widely used in like quantum optics, and also used in like describing the relaxation of the qubits itself. So at the end of the day, you can also rewrite this in the cross formula for this, and this will lead to so-called CPTP map, completely positive and trace preserve map, CPTP map. And so one big challenge is that unitary, the qubits are unitary. If we assume that we have 4 total qubits after all do this quantum error correction, then we have unitary qubits. But the dynamic itself is non-unitary. Then you just think about how to encode this non-unitary on the unitary gates. And this needs to actually different favor of technique how to do this in encoding. So encoding of this non-unitary into unitary. So at a high level, we can think about this so-called dilation method. So that at a high level, so it's kind of reverse engineering compared to the classical method. On the classical, in the classical algorithm, because the entire system is huge, so you consider like spin relaxation in nuclear bath and photon bath. The entire environment is huge. We have many degree filters in the environment, so we cannot treat them all exactly on the equal footing. This is why we have this open quantum dynamics. So we trace out all the environment degree filter and only do the dynamics of this system of interest. But if we put them on quantum computer, this is challenging. Now we are doing kind of reverse engineering, as I said. So when we do the encoding, we put this non-unitary dynamics of this small system into a subspace of intended herb space including environment. And definitely this environment can be smaller than your original true environment because you can do some compression on the environment. You're using like SVD, single value decomposition technique. But at a high level, that we are actually putting back of this small system into an extended Hertz space of enlarged system plus a single qubit to mimic the bath. So this will introduce kind of a challenge. Now we need to use more logic qubits to mimic the bath to study this dynamics within the small subspace of its intended Hertz space. And logic qubits are very expensive. We need to very high overhead to mimic logic qubits without quantum error correction. At the end of the day, then we need to encode them, encode the environment without this asynchrone logic qubits. So by doing this, actually this will introduce two twofold of complexity. First, we need a larger overhead of the qubits to mimic to make up high fidelity logic qubits, and then we need to encode the environment engineering environment with an ancillary qubits to mimic the non-unitary dynamics. So this will have this twofold complexity, increases the overall resource on the qubits. Then our naive idea is that can we think about a different way? Can we reshape the noise from qubits to mimic our target dissipative dynamics? Because fundamentally, either my target dissipation or the intrinsic noise of qubits, they are all open quantum systems. They can be described in the similar formula with this cross formula, for example. Actually, they have the same format. Definitely, they have different dissipation channel. Then, can we just do different engineering? So in conventional co-EC picture, you treat all the noise as a container, and then you introduce like a larger redundancy of the physical bits to found a small code space out of this redundant physical bits to make up one logic qubits. But now, can we just do a kind of do partial quantum error correction? The idea is that because that all can be described in this cross formula, that all stay in this kind of same hyperspace if we have the same size of system. So can we just suppress the wrong channel, which is out of my dissipative channel, and then only do this quantum error correction on this undesired channel, but keep the other desired channel, then we can mimic our target dissipative dynamics. So this is the main idea. And from high level, actually, so all this co-EC quantum error correction cycle can be regarded as one CPTV map. Actually, I have more detail here. So if you do this quantum error correction, you do syndrome measurement, you have some redundant physical bits to enlarge hyperspace, and then find the code space outside of this enlarged hyperspace. But from high-level physical picture view, all this quantum error correction will create one CPTV channel, and you will mitigate all other channel other than utility. You will only keep here. You will do this recovery code from R according to the syndrome measurement to mitigate all the channel other than this identity policy channel. But at the high level, this picture is still kind of a CPTV map, but to a very specific like two channel. One identity channel. Then the idea is that can we do some twist on this recovery code? So instead of do the recovery on all undesired channel, we do some modification on the R, this recovery code itself, and to use from a different R to mimic my target distribution. So that's the idea. And then the idea that okay, now we don't do this full quantum error correction. We do some twist on the R, and we shape the R and found some kind of linear combination of my logic dissipation channel to make up my dissipative dynamics, my target dissipative dynamics to mimic my open quantum system. So that's the main idea. So the only difference is that we do need to be the difference on the recovery code. We shape it instead of correct. As I said, instead of correct all this undesired distribution channel, we only do the correction. We do the shaping on the recovery code R itself, and found linear combination of this distribution channel to mimic my target dissipation. And we have actually we can prove that. So because overall, no matter like a partial quantum error correction or quantum error correction, is kind of a CPTV map. And if we use this core state channel duality, so we can, in particular, we'll be more convenient to prove this with this choice state channel. So anyway, so we can all this channel, the distribution noise channel from the logic qubits. So you can make a linear combination of these channels to mimic any arbitrary CPTV map, and then my target dissipation is also lying in this space. And eventually, because if we do coarse state channel duality, and if we expand all the dissipation with a choice channel, coarse channel, so this can be kind of a convex optimization problems within this coarse channel picture. And we can prove that we can guarantee by minimizing by this channel distance between this cost function and my target dissipation, I can find R to achieve a kind of a desired accuracy to mimic my target dissipation channel. But overall, so when we do this optimization, at the end of the day, this only kind of a convex optimization problem over R in the course state channel picture. And then actually we have different strategy to do this. One way that we have strategy one so-called this is to partial quantum accuracy. So we do some calibration on the noise. So first we do calibration on noise to learn the noise channel from your physical bits, and then we have, because now we know the picture. Then so when we do the recovery code, so on the quantum accuracy. So instead of just correct all the error you show up in the central measurement, now you do need to build a twist on this procedure. So you based on based on your calibrated noise model for the physical bits, then you can get a noise channel for this logical bits. Then I will only first only remove this undesired channel, and for the desired channel, because there cannot guarantee the perfect match. Even though the channel may be not in my target dissipation space, the coefficient may be different. This is why I need to do a little twist on the R for this, even for the desired channel, and for the undesired one, I just according to the central measurement to correct it. And in this way, actually, we can make the code distance smaller than conventional quantum error correction. Because for conventional quantum error correction, you need to correct all the error, and then you need to make the code distance longer enough to make your logical bits error probability smaller than certain limit. But now, because I only need to remove this undesired channel, I want to keep the desired channel, but do some twist on it. So I don't need to have long distance as a conventional co-EC, so I can do little twist on the code distance. So this is a kind of quantum circuit. So the main difference will be in the recovery stage. So instead of just pure depends on the central measurement and do the recovery, now I will have the other information, this RKS, as informed from my calibrated noise channel from the qubits and also my targeted dissipation. So this is R we will be we will find from this convex observation problems. So this is the difference. Now with this, then we can to do this partial quantum accuracy and to mimic my target dissipation. But the one disadvantage is that we need to assume some noise model for the qubits, and we need to do the calibration. And then you may comment also, as long as you need to rely on any model to approximate the noise from qubits, maybe not so interesting, because any approximation cannot be exact. Then this comes to another strategy. Can we then still do kind of regular quantum error correction? Now, the only difference is that we will do kind of a post-correction logical programming. So this is very similar to the conventional co-EC. So you first do regular co-EC to remove all the error, and after we removed all the error, because we have this ancilla qubits and this ancilla qubits can make up the logical dissipation. In your conventional co-EC, you just found the recovery R from the central measurement and correct all the noise channels. Now you will after this, because this space is still there, this noise channel is still there, you just don't use it. So but now you can reintroduce some coefficient R here, do the so-called post correction logical programming, meaning that after we correct all the error from this quantum co-EC step, then we will re-inject some noise into this logical dissipation channel encoded in the ancilla qubits. Again, this will be another like a convex observation problem, and we can find R to mimic our target dissipation. And then the advantage is that we don't need to assume any noise model for my physical qubits. And this is roughly the quantum circuit, and this is again very similar to the conventional co-EC, but now we'll do an additional step. So In conventional code-EC, you do this recovery code based on your center measurement to correct whatever error appear in your content circuits. But here now we have additional step. We do this post-correction logical programming to re-inject my target dissipation channel. And then the advantage is that we don't need to assume like any noise model for my physical bits. I will just do regular code-EC and correct all the error show up in my content circuits, and then we'll do post programming. But the downside is that now, because the first step will be the same as the conventional code-EC, we cannot save the code distance. So this will not reduce the physical code bits overhead to mimic the logic code bits. But still, this will be advantage than doing like a dilation for encoding the environment information, because now we will re-inject the noise or dissipative channel introduced by environment by this additional kind of recovery procedure. We don't need to require like ancilla code bits to mimic the environment. So this will still be an advantage than like encoding this non-unitary dynamics into unitary logic code bits without. Now, even with this, we don't need this ancilla logic code bits to mimic to mimic the environment. So that's still advantages than compared to other kind of encoding of non-unitary dynamics. So I can skip this one. This is particular for this strategy A, where we do this partial quantum error correction, because now we only need to mimic the environment. We are reshaping the noise channel to mimic the environment. Then we don't need this same code distance as the conventional code-EC. We can do some lift on the code distance. This is the cost function to determine the code distance we needed for this partial quantum error correction. In particular, that we can get to this kind of physical code bits overhead advantage compared to conventional code-EC. So we can make the code distance shorter compared to full quantum error correction if we do this partial quantum error correction. So for example, this is like a logic error rate of the surface code, assuming certain like switch code for the error, and if you need a high fidelity logic code bits, you need thousands or even 10,000 physical bits to mimic this to make up high fidelity logic code bits. But now if we do partial quantum error correction determined by your target dissipation rate, then you can end up with different like physical bits to mimic up this target dissipation to reduce the code distance. Then you can save a lot on the physical code bits. So here is one simple numerical example. So this is based on like a very torus model, like a two-side spin realization problems. This can be used to mimic either spin realization or even like a coherent acetone transport in organic crystal. So, and this is one numerical example. We use a different strategy. And so this is the dynamics of propagation, and this is dynamics of the coherence. So overall, either strategy A or B, this noise aware partial quantum error correction or post correction method, we can get a very high fidelity simulation of this target dissipation by reshaping the noise. So as I said, if we use this strategy A, which is partial quantum correction, then we can save a lot on the code distance. So and then this will translate to saving on the physical code bits overhead to compare to regular code-EC. And for strategy B, because this is post-correction method, now we need to use the same code distance as regular code-EC. So the code distance will not be reduced. But I said, because now we inject this dissipation channel into this quantum error correction procedure. So we don't need to require a standard code bits to mimic the environment. So this is still an advantage compared to fully correct the code bits and then do this the encoding of non-unitary into unitary gates with standard code bits. So that's still the advantage. But here this is already one simple example to demonstrate this method really works on code bits. And then now we are actually working on to implement this code on this method into more scalable code and to demonstrate on real hardware. But overall, this is a kind of a high-level picture how we can reshape noise into our target dissipation, and how and demonstration on some simple torus model how it could work in real simulation of this open quantum system, and we estimated that by reshaping the noise, by making use of noise from qubit itself, we can significantly reduce the physical qubits overhead for this dynamics, and we expect that maybe we can achieve early quantum advantage in either early photonic regime or in the photonic quantum computer age. So this was a kind of vision where we could maybe achieve early quantum advantage on the dynamics. But I want to emphasize that actually this can be used beyond the dynamics of open quantum system. And in particular, actually, you can even use this one to prepare the ground state, because if, for example, you can set your system to arbitrary state and do this discrete dynamics, eventually will decay to low energy state. So this can also be a strategy to prepare ground state as well. So this is why I want to emphasize the application can go beyond this open quantum dynamics. So with this, I want to end my talk, and on the left side is the people working on this project, and in particular have some collaborator with computers, some collaboration with computer scientists. They are working on making the code or making this method, implement this method into some software and make it more scalable than my toys model. And these are some other people working on the previous project. In particular, I have many students from this quantum computer summer school, and this was something I want to advertise. So if you are students, consider this opportunity. So every year we will host this quantum computer summer school. So roughly we will select like roughly 20 people out of more than 500 candidates. So it's a good opportunity to learn quantum computing, no matter what your background is. So with this, I want to end my talk. Thank you.
Yeah, so could you comment on possible black hole sort of system in the open system simulations like FIMOCA we heard about in electronic structure, but any easily scalable paths to quantum or demonstrating quantum advantage in simulation of open systems?
Yeah, same one. Just make the size of the system larger. I think the spin realization may be the best one. This is why actually I choose this one as the towards model. Here I only use 2 sets, but you can increase the number of sets. And here I only consider pure defacing, but then you can also consider realization. So this one actually is a simple, I would say maybe simple example to demonstrate the quantum advantage. In particular, you can make an interaction more complicated than this one and increase the number of sets and make maybe like 2D lattice. And actually, this is challenging on quantum computer. Actually, the one thing I forgot to mention that dynamics is more challenging than ground state. For example, like DMRG, you can simulate for Merkle on HPC, but if you do dynamics, even you start with some localized wave function, eventually, in general, many quantum systems, the entanglement will spread during dynamics. I mean that if you do like a time-dependent DMRG, you need to make your bound dimension linear growth with the time propagation. So that will become one of the more expensive on quantum computer. So this is another advantage we'll do in dynamics on quantum computer. This we don't need to consider the bound dimension growth issue here, and also this is challenge on quantum computer. So with this, I guess with this model, just make it 2D lattice, make the interaction more complicated, and add like realization beyond pure defacing. So this can be really sweet spot to demonstrate this idea to scalable, kind of to demonstrate scalable simulation of this method. Yes.
Yeah. Well, first, it's a very interesting idea to reduce the resource. And my question is, when you do error correction, do you consider like additional errors associated with answer that exceeds error correction, which might also modify the effective challenge?
Yes. So that's good question. But at this moment, I assume there is no error on like error detection stage, and I only assume there is error on my code space. But in principle, when you do this quantum error correction, every stage can have error. Yeah, so that's something we will consider next step. Because for this one, we just want to have a prototype demonstration in this work. But in next, we will consider more like a practical issue. And also in the next, we will consider how we further consider symmetry in the distribution channel to further reduce the scaling. Yeah, I didn't mention the scaling of this, but actually we have proof on the scaling of this on finding the R. So it's kind of polynomial, but in the next, we will more like a practical issue to further reduce the scaling. That's Yes.
So you have some method to choose wrong channels and the right channels that then you map to your target problem.
Yeah.
Is there a method to choosing the right and wrong that reduces the cost of that map?
Oh, so you can just make a one cost function because you lose. I mean, for my target distribution, if this is why we mentioned I mentioned that we use the core state channel. So with this core channel, so it's kind of a linear combination of all these core channels. Then you can also you have another expression for your physical qubits or logical channels. So you can derive the channel distance as a cost function to minimize that one to find the R. Yeah. So that's the kind of channel distance is the cost function we minimize.
Any last question? If not, let's thank the speaker again.
Thank you.
So apparently, okay, he's like it's like a high.
I don't forget one of them.
Very quiet.
Oh.
Anyway, yeah, so he was saying.
I mean, I guess there's a few places it could go.